Hello everyone, welcome to the Chapter 5 review. So the goal of this review is just to help you out with some problems that maybe you haven't been tested on yet. So it includes the sections 5.1, 5.2, that was all the triangle stuff that we talked about, law of sines, law of cosines, and also the polar equation, polar coordinate stuff. So I just wanted to make a little bit of a review, a little bit of a video to help you and do some problems of that variety. Doesn't necessarily mean anything on the exam would look like one of these, but this should give you a good idea of the kind of things you might see, the kind of problems that could potentially show up. Problem 1. So two rival sailors, Althea and Kenneth, are searching for glorious treasure. So they're both traveling towards it at the same speed, and they're 120 miles apart. And so if the angle's centered at Kenneth, so that's saying like, you can't see my cursor very well, but like this part of the angle right here, that's in that part of the triangle. If that angle is 58 degrees, and the angle centered at Althea, so this angle right here is 71 degrees, how far away is each person from the treasure? And so then the more important question for the two of them, who will get there first? All right, so I've drawn the picture down here mostly. I need to fill in my angles. So the angle centered at Althea is 71 degrees. The angle centered at Kenneth is 58 degrees. And the distance between the two of them is 120 miles. So I'm going to write down that unit just because it doesn't hurt. And now what we want to know is we want to know how far away is Kenneth. So let's call that K. That'll be the distance that Kenneth is away from the treasure. And how far away is Althea from the treasure? So let's call that A. And so what we want to do is we want to solve for A. We want to solve for K. That'll tell us how far each of them apart. And then once we have those two pieces of information, we can find out who's closer. Given the picture as we have now, we can actually already figure out who's closer. That might be a fun exercise for you to think about before we go through. But let's work it out. So let's work on finding K first. And so we have to use the law of sines. The reason we have to use that is because we have a pair, even though it's kind of secret. So I don't know this side, but I know the angle. I don't know this side, but I know the angle. So there's not an immediate pair there. Because at face value, I don't know that top right angle. But actually, I can find it really easily by just taking 180 minus the two of these. And so we put that together, we get 120. That makes 129. And so we get, I don't trust myself to do that kind of math at the moment. I'm putting it in the calculator. 51 degrees. Okay. Glad I double checked because I was about to say 61. All right. And so now we have everything nice and squared away. We can find K. How do we do that? We use the law of sines. So whenever you know a pair, so here I know side and an angle pair, I can use the law of sines. Generally, at least in my opinion, that's easier. So I'm going to say K over sine of 71 degrees equals 120 over the sine of 51 degrees. And we can solve this for K. So you might see that the law of sines is usually kind of upside down to this. You're not going to get it wrong. If you started with this equation flipped, it'd just be a little bit more annoying to solve. So I'm going to start with the K on top because that's what I know that I'm looking for. So now I'm going to multiply both sides by the sine of 71 degrees times sine of 71 degrees. That makes K equal to 120 sine of 71 degrees divided by sine of 51 degrees. Now I just pop this into the calculator. one thing to be a little bit wary of is make sure your calculator is in the right mode. So here we need to be in degree mode, otherwise we could get like some crazy answer. So if you're getting something that doesn't make sense, there's a good shot that's why. And so here I'm always going to assume we round to 2 decimal places for this review. So I got 149.998. What happens in that situation when you get like 0.99 and you need to round up is you still round up at the decimal like you would, but you include those zeros. So I'm not going to promise that this comes up, but what this says is Kenneth is almost, or roughly, 146 miles away. All right, 146.00 to be really precise. So that's because if we got something like Althea's distance was 146.01 or 49, we would remember, oh, okay, right. We were almost right on the dot at 146. That's why you write those zeros. I don't want to get into too much of a tangent on that, though. Now we find Althea's distance the exact same way. So A over sine of what's across from A, 58, is equal to same thing on the other side that we started with last time. 120 over sine of 51 degrees. So then A is equal to 120 times sine of 58 degrees. We're going to multiply that on both sides again. Put this into the calculator. So 120 sine of 58 divided by sine of 51 gives us approximately 130, rounding to 2 decimal places, 0.95. And then in both of these cases, the answer is in miles. So we know Althea is about 131 miles. Kenneth's about 146 miles. So our final answer is Althea will get there first. And it also asked us for the values. And so there they are. Kenneth is 146 miles away. Althea is 130 miles away. And if they're going at the same speed then, in a straight line, then we know Althea is going to be the one who gets there first. Problem 2. Problem 2 gives us a triangle, and it asks us to find all of the sides and angles of it. So what do? Well, let's go to the tablet where I've drawn it. And it gives us A equals 6, B equals 7, and then the angle that's in between is 101 degrees. And so we want to find beta, we want to find alpha, we want to find the last side C. So one option is, you might see I've already written it, that we could just memorize the situation that it's sine angle side. If that works for you, then all the power to you. Or I like to think about it more binarily, insofar as I don't have any pairs here. C, I don't know, but I know the angle across from it. I know A, but I don't know the angle across from it. Same story for B. So I don't have any pairs. In that situation, the only thing that I can do to make progress is find the missing side. I can find C. There really is no immediate way to find alpha or beta that doesn't go through finding C first. So here I need to use the law of cosines. So I get C squared equals A squared plus B squared. It starts out looking like the Pythagorean theorem. And then we say minus 2AB cosine of 101 degrees. So that's our law of cosines. We put C on its own side. Then we put the angle across from it. It kind of like sandwiches everything with the other two sides. And here, technically, if I'm writing the formula, it's gamma. Because now I plug everything in because I know A is 6, B is 7. So I put all of that together. And then put that into the old calculator. Right, calculator loves to do this. Sine 101. We make sure it's in degree mode. And the calculator spits out that c squared is roughly equal to 101.03-ish if we're rounding to 2 decimal places. Of course, we might as well take the number we get, so I get like a big long 8-digit number. I might as well take all of this and just take it to the square root. So I get c is approximately 10.05. Okay, so that's side length c. And one thing I like to do, I call it a sanity check, is like, does this number seem reasonable? Well, c is across from an obtuse angle, so c should definitely be the biggest side of that triangle. And so therefore 10.05, that seems pretty reasonable. If I got a number that was like 2 or 5 or something like that, I might be a little bit weirded out. But 10 seems okay. So there's my number c. Now I need to find alpha or beta. Doesn't necessarily matter which one. So we're just going to find one. I'll choose beta. And so how do I do that? I could use law of cosines again now that I know all 3 sides. But that's a little bit of a project, right? Law of cosines is a lot, we just saw, especially when you need to solve for the angle. So I'll use law of sines again. So I'm going to use this pair, 101 degrees and 10.05. So sine of 101 degrees over 10.05. That's a pair there. And now if I want to find beta, is sine of beta over, and then b is 7. And now we're going to find beta. So move things around. Sine of beta is 7 sine of 101 degrees divided by 10.05. Solve this guy for beta. So this is 7. Actually, it is. If I want to get beta by itself, I need sine inverse 7 sine of 101 degrees divided by 10.05. I plop that into the calculator too. So 7 sine 101 divided by 10.05. And I get that beta is roughly 43.14 degrees. Okay, so we have side C, we have angle beta. So now we just need to find alpha. But now that we have 2 angles, finding the third is really easy because this is just a triangle. So this is 43.14 right here. And so how do I find alpha now? Well, alpha is 180, and then subtract off the other 2 angles, minus 43.14. This one in theory I could do, but I have a calculator right in front of me, so I might as well use it. And I get alpha is about 35.86 degrees. 0.86 degrees. And the other 3 sides of the triangle were given to me. So I was given 3 parts. I found the other 3 parts. And that's how you solve the entire triangle. If you can use law of sines, I generally prefer to do that. I find it just easier. Otherwise, you have to use law of cosines. But once you use law of cosines once, you can use law of sines to find the next angle. Problem number 3. So use this graph below to help us graph the polar coordinates. So this would give you an idea where 30 degrees pi over 6, 60 degrees pi over 4, all of these kind of things, where these would go. There should be a 45 here. So on the exam, you might see something that tells you degrees. You might see something that tells you radians. Probably not both, so you probably want to be able to convert from one to the other. Here, everything is in radians. So we want to graph 3 comma pi over 3. So A is 3 comma pi over 3. And now remember, with polar coordinates, the way that they work is we have our polar axis. And the idea is we would have our normal tick marks that denote distance. And whatever I tell you your distance is, that's what circle you're going to be on. So when I say 3 comma pi over 3, that means I'm going to have to land somewhere on this outside circle. How do I know where that I land? I make an angle of pi over 3. So if I had the picture, I could have just used that. So instead I have my wish.com version of that circle. But we can find the angle pi over 3. And we know that the point is going to be right there on the circle. So I know the angle. I know that. And so this is 3 comma pi over 3. Right? And I got that because this angle right here is pi over 3. If we take a look, part B is asking us for -1, 7 pi over 6. And so this gets done in the same way, or a very similar way at least. So I figure out where 7 pi over 6 is on the unit circle. And that's a little bit more than half a rotation. And so now what does that -1 do? So if it was a positive 1, we would put the point right here. But because it's negative, we're going to walk it backwards and go in the other direction. So that is -1 comma 7 pi over 6. So that's how we graph that. It needs to be on this circle, that innermost circle, because it has a radius of -1. And now finally we have 2 comma minus pi over 2. So you have a few options here. Hopefully you're comfortable enough with the unit circle that you can figure out what minus pi over 2 means, right? Namely, instead of moving clockwise by pi over 2, you're going to move counterclockwise instead. So here's minus pi over 2. If you're only good with unit circle angles, you could retrain this. You could change it to something else. So C we see is 2 comma minus pi over 2. But in polar coordinates, what we could do is we could add 2 pi to that and get 3 pi over 2. So if I wanted to be able to graph this where the angle is in the unit circle, I could just take the angle I was already given and add 2 pi to that. And so now all the 2 is doing is telling me how far to go in that direction. And so those are my coordinates. Problem number 4. Convert the rectangular coordinates 2 comma minus 2 into polar coordinates. So here what we would like to do is we've got our normal coordinates that we're used to, and we want to write these instead as a pair of polar coordinates. So how are we going to do that? Well, we have the rectangular coordinates 2 comma minus 2. How do we convert to polar? So to convert to polar, we need the equations r equals the square root of x squared plus y squared, so we won't have any trouble finding that radius. And we need theta is equal to tan inverse y over x. Okay, so these are the equations that we're going to use. The r one is pretty simple and straightforward. R is the square root of 2 squared plus 2 squared. R is equal to the square root of 8. To be honest, on the final, that would probably be fine, but let's just make sure, right? This could be a multiple choice question. We could simplify it on you. And it's good to be able to simplify fractions. So the biggest square inside of 8 is 4. So I'll rewrite this as 4 times 2. We can split up the square roots. Whenever you're multiplying, you're allowed to split up square roots. And so r is equal to 2 times the square root of 2. So the radius is generally the easier one to find. It's just straight plug in. Theta is a little bit more difficult. So theta is tangent inverse of y over x. So we have minus 2 comma 2, which means theta is equal to tan inverse of minus 1. But now tan inverse of minus 1, what should that be? Well, we could go to the unit circle. So the way we would solve this is we would look at the unit circle and we would say, where is tangent of theta equal to minus 1? And so tangent is sine over cosine. If tangent is negative, that means we're either in quadrant 2 or we're in quadrant 4, because sine and cosine have different signs. But we can actually figure this out via the point we were given. 2 comma minus 2 is down here. So this is in quadrant 4. And so that's going to help me find the right angle. Because in particular, when I peg my point on the unit circle, they need to have the same value, but with opposite signs. And so if we look on the unit circle where that happens, we get root 2 over 2 minus root 2 over 2. And so that angle happens at 7 pi over 4. So theta is 7 pi over 4. And now we wrap that all up into one nice neat little package, 2 square root 2, comma 7 pi over 4. And those are our polar coordinates. And so this is how I would direct somebody to walk to the point 2 comma minus 2. Instead of saying walk 2 miles, feet, whatever unit we're using, instead of walking like 2 miles to the east and 2 miles south, I could just say point southeast and walk, probably multiply on a calculator to root 2. Walk that distance away. Problem number 5. So now we want to go the other way. We want to convert the polar coordinates to the other direction. We want to go polar to rectangular. And so our polar coordinates are 5 comma 7 pi over 6. And so converting from polar to rectangular is, at least in my opinion, easier, because it just boils down to 2 formulas. We need, if 5 is r and 7 pi over 6 is theta, then we just need the formulas x equals r cosine theta, y equals r sine of theta. Okay. And so how do we do that? Well, now we just plug in. So I say x is equal to 5 times cosine 7 pi over 6. We plug that in. We look at the unit circle. We figure out what the x value is at 7 pi over 6. And that is a minus square root of 3 over 2. And we probably want to leave that as an exact answer. And the reason for that is if you can find an exact answer to an equation or a question, you can always find the approximate answer just by plugging in. And so now y is r sine of theta, so 5 times sine of 7 pi over 6. that's equal to 5 times minus a half is minus 5 halves. And so that's what we're going to put together. That's our final answer. We have minus 5 on the square root of 3 divided by 2. That's our x value. Minus 5 halves. That's my x value. And that's our answer. And so this is enough for the problem. But I do want to take a moment to talk about like the very practical reason why there's an argument here that's really important. Why is this r cosine theta, r sine theta stuff? This shows up in engineering and physics a lot. I really can't hammer that too much. That say you know this length r, and you know what angle it makes with the horizontal. So this is a situation that can come up all the time in physics, can show up all the time in engineering. And so what's going on? Why is this the case? Well, it's because we know that cosine of theta, here's theta, cosine of theta would always be x over r because it's adjacent over opposite. Sine of theta would always be y over r. And so breaking something down into components like this, you might not do polar coordinates all the time, but finding we call it the horizontal component, how much have you done in the x direction, the y component, how much have you gone in the y direction, is actually a pretty important tenet. It's a very baseline thing to have if you're in physics, engineering, especially if you're in architecture. So I just wanted to point that out because it's very important. We take pre-calculus usually because we're taking classes after this. And this is one thing that really does show up all the time later, is breaking it down into vertical and horizontal components. Problem 6 asks us to graph the polar equation r equals 4. And so here the big thing to know, this is kind of fundamental to polar coordinates, is you say, okay, I have I'm used to the iPad making that a straight line for me. You have your polar axis, right? It faces due east or straight right. And the idea of polar coordinates is any tick mark, any radius represents a distance. And in fact, the reason why it's called a radius is because if you have just r equals 4 like this, if you have r equals a number, literally all that is it's a circle with that radius. So I go purple here, and then in theory I draw a perfect circle. In practice it's not very good. So let's try that a little bit better. But the major thing is it is a circle with radius 4. Okay. Circle with radius 4. Problem number 7. So here we're asked to graph the polar equation theta is equal to 2 pi. So now we know what theta is, and it doesn't say anything about r. And so in polar coordinates, whenever it tells you one piece of information but not the other, then that means that one that it didn't tell you is allowed to be anything it wants. So for example, here we have theta equals 2 pi over 3. R could be anything. So I didn't say anything about the radius, didn't put any rules on it. And so if I don't do that, it's allowed to be free. And so how do we decide what this graph looks like? Well, normally on the unit circle, if we were graphing 2 pi over 3, we would say 2 pi over 3 is like somewhere in this general direction, right? This is roughly the angle 2 pi over 3, right? Not looking for perfection, just it's more than a half turn, more than pi over 2, but it's still going to be more up than out. And so all we do in polar coordinates, actually, in fact, let me even write that angle, is in polar coordinates, we just go and we draw a line through it. So the idea now is any point on this line makes angle 2 pi over 3 with the x-axis, except down here we kind of have a little bit of a negative radius. But that's the idea. Theta equals a number is just a straight line through the origin. Problem 8 is a little bit more complicated. So now we want to graph the equation r equals 4 times sine of theta. So here, one thing I would keep in mind is we can always just plot points if you don't know. So if you're sitting on the exam and you really have like no idea what this could look like, you could make a big list of all the points on the unit circle. So you could say theta equals 0, pi over 6, pi over 4, pi over 3, and just plot it by hand like that. It probably would be a good idea to have at least a general idea of what all these look like. So sine and cosine, sine and cosine, they both look like circles. And those circles are touching the y or x-axis. And so here, if we have r equals 4 sine of theta, to be honest, the way that I would do it on the exam is I would plot out 0, pi over 4, pi over 2, 3 pi over 4. You can go back to pi if you want. And the idea then is we should get the whole picture of what's going on from this, if we know what the general shape is. So I see 4 sine of theta. Maybe I don't remember exactly what's going on, but I know it's like somehow a circle that's moved a little bit. So now I just plug these thetas into 4 sine of theta. And so I get 4 times 0 when I plug in 0, because sine of 0 is 0. Sine of pi over 4 is square root 2 over 2. So we get 2 times the square root of 2. Sine of pi over 2 is a perfect 1. 3 pi over 2, we kind of arc back down. We get 2 on the square root of 2. And then 4 times sine of pi, sine of pi is 4 times 0 again. We go back down to 0. And so now, armed with this information, I can draw my polar axis here. 1, 2, radius is 4, so let's go out to 4. And now I can plot point by point. So 0, 0 goes right here. Pi over 4 says it should be on this angle. And then 2 times the square root of 2 is roughly 2.8. I could put that on my calculator. So that would go right about here. Pi over 2 comma 4 puts me right up top. Right, here's pi over 2. So I go about 4 up. I would make like a circle like this. And that's how I got this number as well. So actually doing this, I can see that point might even be a little bit off. And then we do the same thing for 3 pi over 2. Now 3 pi over 2 is over in this direction. 3 pi over 4, sorry. 3 pi over 4 is over in that direction. And so normally 2 root 2 would say plot it here. And for some reason I was thinking the radius is negative. But because the radius is positive, we do honestly just plot it right there. And so now I remembered it was supposed to be some sort of circle, maybe not exactly what it looked like. But with all the information I have now, I can put all the pieces together. And I can draw a circle like this. Okay. And again, we're not necessarily asking for perfection, just this is what this should look like. It turns out to be a circle with diameter 4 that sits on top of the x-axis.